Hi, I'm Ben-Yaakov. This presentation is entitled Capacitance Definition of Voltage-Dependent Capacitors, the Fundamental Q as a Function of V curve. When it comes to a linear capacitor, the definition of capacitance is very simple. It's like charge over voltage, Q over V, and the relationship when you plot it is a straight line. Well, in the case of a nonlinear capacitor, and I'm concentrating on this video on capacitors which are built around the ferroelectric dielectric and the so-called class 2 and class 3 capacitors. In this case, these capacitors are nonlinear and they are voltage dependent. The information that is supplied by the vendors, by the manufacturers, is shown here. We see here capacitance as a function of DC, and in this case the information is actually obtained by this set of measurement in which we have a voltage source in series with a AC excitation. It is a 1 volt AC. This is 1 volt AC in this case, volt RMS. This is the capacitor under test, and by subjecting the capacitor to this excitation, you can calculate by measuring the current and of course taking into account the frequency, you can calculate the capacitance. So here it is, the voltage is stepped, this bias is stepped, and for each point the capacitance is being measured, and this is one set of information. Another set of information which is available from manufacturers is also labeled capacitance. In this case, the horizontal axis is AC voltage. This is obtained by this set of experiment in which you have a AC excitation, no DC. This is the capacitor under test, and the amplitude of this excitation is now being changed from small values to higher and higher and higher values, up to, say, in this case, 2 volt. This is the amplitude of this excitation. And again, by measuring the current and knowing the voltage and the frequency, you can calculate the capacitance for each point. Both of these measurements are made at 1 kilohertz, that is, the signals are of 1 kilohertz frequency. This particular information is from Murata datasheet for this particular ceramic capacitor. It's a 0.47 microfarad capacitor. Now, we see here that there's quite a bit of a change. There's a change here, and here it starts from about 4.7, but then it drops with a bias voltage to about 0.1 microfarad. Now, the point that I like to make in this video is that the most important property of a charge storing device, that is a capacitor, is the function of charge as a function of voltage, which in the general case for a nonlinear capacitor would look something like that. This is the charge, this is the voltage, and this is the relationship between the two. It's nonlinear. In the case of a linear capacitor, of course, this is a straight line. This is the most important point that you can start with. Once you have this curve, you can actually define 3 types of capacitances. The first one I call total capacitance. This will be the ratio between the charge and voltage at any given point. Say at any given voltage, say at this point, the ratio between the charge, this is the charge, and the voltage can be defined as the capacitance, the total capacitance at this point. This is represented by this straight line. Obviously, for any other point, we're going to have another straight line with another slope. The second definition of capacitance, I call it local capacitance. Some people call it small signal capacitance. This will be the derivative at any given voltage. For example, here, this slope here, this derivative, delta Q over delta V, can be defined as the local capacitance in this region. So when you have a signal which is moving this way, then this will be this capacitance at this particular point. Again, for each other point, there will be a different value of capacitance. The third one is the large signal capacitance, which is important when the amplitude is large. That is, there is an excitation, the amplitude is large, and this capacitance is defined as delta Q over delta V. For example, around this particular voltage, there is an amplitude here, and we are moving back and forth on the nonlinear curve, but I can define a linear portion here, segment, which is defined as this large signal capacitance. Again, if the excitation is around 0, we are going to have a line like this, and if the excitation stays here, we are going to have a line like this. So this large signal capacitance is also changing depending on the voltage you are at. So all these are voltage dependent, and they are changing depending on the operating point, on the bias point of the capacitor. Let's see where are we going to use each one of these definitions. The total capacitance, that is the ratio between the charge and voltage, say at this point or any other point, will be useful when we are analyzing cases like a nonlinear capacitor, which is charged, connected via switch to a linear capacitor, which may be charged or not. And then as we close the switch, there is charge being transferred, and the process here is really a function of this total Q and V. So therefore, this would be a case in which this definition will be relevant. The definition of local or small signal capacitance will be relevant to cases in which you have on the capacitor some DC and ripple on it. For example, in a, say, a buck converter at the output, if this is this nonlinear capacitor, a ceramic capacitor, you're going to have DC with AC ripple, and the relationship of this ripple voltage and current of this ripple is according to this local capacitance or the small signal capacitance, that is this slope here. This will be the DC and this will be the AC superimposed. Now this is correct only if the amplitude is small. If the amplitude is large, then you really have to go back to the large signal, which I'm going to talk about in a minute, because you're going to see the non-linearity of the curve. Here, if this amplitude is very small, or here if it's very small, then you can assume it's a straight line. If it is large, then of course there is a curvature, there will be a difference between the value of the capacitance and the actual slope at this point. So there might be a difference between the large signal slope here and the small signal slope here, depending on the curvature and where you are at. For example, if you have very large signal going from here to here, then of course this slope is much different from any local particular slope that you can pick. So this will be the application of this local capacitance, small signal capacitance, when you have DC and some ripple on it. Now, in the case of a large signal capacitance, which I have defined here, then this will be relevant to, say, resonant converters, in which you have large signal, you have a large current, AC current, passing through the resonant circuit, and on the capacitor it's going to be an AC signal, and this magnitude, the amplitude of these signals could be large, so therefore small signal representation is not good enough. You have to resort to the large signal definition, and again this could be with or without DC voltage on the capacitor. For example, if the capacitor has no DC, then of course you are moving from 0 back and forth. If the capacitor does have some DC on it, then of course, say this is the DC, then you'll be moving on this curve. So this is the large signal capacitance, which is a function both of the voltage you're at and the amplitude. As I've said, this is also very relevant to ripple with large amplitude. So let me just reiterate that the most important piece of information about a nonlinear capacitor is this function, the charge as a function of voltage. Once you have this, you can get all the information that you really need for any particular application. Now, in the case of the data given by the manufacturers, we have actually here, this is the local capacitance or small signal capacitance, which is shown here. This is excitation, small signal excitation. Well, it's not that small, it's 1 volt. It would have been better to measure it at a lower amplitude, but this is what we get, a 1 volt RMS. And this is for different value of DC bias, starting from 4.7, then it goes down and down, and as we have said, it goes to fairly low value to 0.1 microfarad, starting from the 0.47. Now this is now the large signal capacitance, except that this is measured around 0 volt, that is with 0 voltage bias. And we have here different amplitudes, and for different amplitudes, the capacitance is changing. Now, this set of measurement is actually related or exactly at this point here. That is, this is the point without DC, and this is the local capacitance. This is measured 1 volt. So if we look at the magnitude of 1 volt, which is here, and this is the value, this point and this point are the same, because this is 1 volt RMS, 0 bias, and this is 1 volt RMS with 0 bias. So these two are the same but all other points are of course different. The question is, how can we get this very important function of charge as a function of voltage? The easiest way is to get it from this information of the local or small signal capacitance. The definition of the local capacitance is the derivative of Q, the charge, with respect to the voltage. Now, integrating this, we get an expression for the charge, which turns out to be just the integral of this local capacitance dV. Okay, so by integrating this thing, we are getting actually Q. And so if we are integrating to any particular voltage, then this will be the Q for this particular voltage. So integration is actually an area here. So for example, for the red area here, this will be the charge for 20 volts. So this is one point in this function. Volt is 20 and charge is this area. And of course, we can do it for all other areas. We'll see how we can do it in a more mechanized way later on. Now, once you have the charge, you can actually get the total capacitance by just dividing the charge by the voltage added. Now, here is a suggestion of how to get the function of Q as a function of voltage by actually SPICE simulation. Well, the idea is as follows. We start with this local capacitance, which is given by the manufacturer. And then we sort of digitize it. We get the values of voltage and capacitance. Okay, so this is the voltage here, this is the capacitance, voltage here, voltage 20, and this capacitance, etc. So this is going to be an array of voltage, capacitance, etc., which is sort of a representing in a discrete way the function. And if I pick the point just between two ends of a pretty much straight line, the approximation would be pretty good. Now, we then take this array and use it to build up a G-table, which is an ABM, analog behavioral model of SPICE. Now, the G-table has a current output, and it has an input, which we call an expression, and this input is then multiplied by the array. So any given input will be a given voltage, which will produce a given capacitance, local capacitance. And G-table will produce a current. And then we can take this current, pass it through a capacitor, which is forming this integration that we need. And therefore, the voltage on this capacitor is actually the charge. Now the excitation should be voltage, just a ramp, and ramp which is changing with time linearly. So any given point here is a voltage, and this voltage again is translated or related to a given capacitance, which is producing a current proportional to it, and then generating this voltage, which is Q. So this is actually performing this integral of the capacitance as a function of voltage with respect to the voltage which is fed in. Now, another issue that I like to bring up is energy. How much energy is actually stored in a non-linear capacitor? Now, it is not CV squared over 2, not to mention the fact that we don't know what is C to pick up so many capacitances around, but this is incorrect for any of them. It is also incorrect for this. So what it is this integral of V dq. This is the definition of energy. It's coming from the definition of power, which is P is equal to V times I, and I is the Q dt, for which you get this expression. So energy is this integral. Now, this integral is not easy to get it directly. As it turns out, this integral is this red area here. So, in order to get this area, to get this energy, we can take the difference between this rectangular area, this one, which is Q times V. This is V and this is Q. This is this area, the blue one. Subtract from it this area. And this area is the integral of Q as a function of V, of course, dV. This is this area here. This is this area here. So the difference between the rectangular area and this area will give us this energy. Okay? And we can do it in a similar way that I've shown before. In fact, I'm going to show it in a somewhat different way. You can get it very easily with simulation. So let me just demonstrate how to get all these parameters by simulation. We start off with this local capacitance as a function of voltage. This chart, by the way, is a result of measurements that we have actually made on a capacitor, or this particular capacitor we are talking about. And then we digitize it to get this array. And here it is. This is now the G table. Here is the array, the voltage, capacitance, voltage, capacitance. This is this local capacitance, voltage, capacitance, etc. up to, in this case, 65 volts. Now, this is the array. The input or the expression should be a ramp, and I'm just using time. SPICE or PSPICE recognizes time as a variable. So as you start the simulation, this variable starts to increase as time, as a function of time or as time, and therefore you actually feed a ramp to the G table. Now, since I've omitted the micro from here, this is like 0.5, should be 0.5 micro and 0.48 micro. I'm passing this current through a 1 micro ohm. So this is just setting up the units right, the scaling right, and I'm getting now CD back. So there's nothing special about it, because what I did, I took the information here, got the array, and then reproduce it. What is nice now that I can take this is now a voltage, which is, that is CD, the local capacitance is coded into voltage, and integrate it to get the charge. Now we can use the SDT, this is a operator that PSPICE has, and just get the integral of this thing, starting with no initial condition, everything starts from 0, and I'll get here Q. And now I'll take this Q and use it in order to get this area. And again, this area is this rectangular area here, which is Q over V. This is Q over time. V is decoded by time. And I'm subtracting from it this portion here, this integral here, this integral, and I'm getting the energy. So with this very simple circuit, starting with the array, this is the key point, of course, I'll get all that I need. And here it is. This is the original data. This is the reproduction of the data. This is now the local capacitance in farad. This is volts because everything is coded in voltage. This is seconds, so this is also volts. And this, of course, is exactly like this. There's no big deal here because I'm just reproducing these points, which is the Q, which is the integral of this thing. And as I integrate it, this is what I'm getting with initial value of 0. And this is now the integral of the local capacitance producing the Q. So this is now the most important curve, as I mentioned earlier. This is now the voltage, and this is Q. So this is the charge as a function of voltage of this particular capacitor. And the slopes here are those that we talked about earlier. Now integrating this thing and then subtracting, as we have seen earlier, it from the rectangular area, we get the energy. This is now in joules, and like this will be a 0.5 millijoule here for this capacitor when being charged to say 55 volts. Okay, so this is a way to get all this information as we might need it for any particular application. Let me move now to another issue, which is hysteresis. Now, it has been shown in this paper, hysteresis measurements of multi-layer ceramic capacitor using the Sawyer-Tower circuit. Let's not worry about the Sawyer-Tower circuit, which is a method of measurement. Let's just look at the output. And the output, again, is charge and voltage. Now, in this case, however, there is a continuous excitation of an AC voltage. The voltage here is plus minus about 2 volts, and this is the charge that is being measured. And then we see here something very typical of hysteresis, and this is what, in fact, these authors say, that this is hysteresis measurement. Well, the question is it really hysteresis? Well, the reason for my doubt is that if you just take a linear capacitor, add to it a linear resistor, look at it as a capacitor, a linear capacitor with ESR, okay? And then feed a AC signal to it. Take the integral of the current for Q, and then plot Q as a function of V. This is what you are getting. This area here is the loss, the energy loss per cycle of this circuit. Looks like hysteresis, but it is not, because this circuit has no hysteresis process or phenomena associated with it. This is just a simple capacitor and a linear capacitor and a linear resistor. So we get this curve, which is, of course, very similar to this curve. Here we have some sort of saturation. That's a different story. Ferroelectric material is getting to saturation. I'm talking about this hysteresis area. So the question is whether what is observed here is really hysteresis or not. It is my opinion that this needs more study in order to decipher this question, which is not trivial at all. Let me now move to the final point that I like to show, and this is a way to analyze a case in which you have a linear capacitor, which is charged or connected via switch to a nonlinear capacitor. Both of them could be charged or not, just one of them. And the question is, if you start with this linear capacitor with a certain voltage and a certain charge, and then the nonlinear capacitor will have a certain voltage and a certain charge, and then you connect the two, what will be the end condition? That is, what will be the voltage and what will be the charge in each of these capacitors. So this is the question that I'm posing. Now, the easiest way, in my opinion, to solve this is graphically, starting with this nonlinear capacitor with the Q as a function of V curve. I can plot this curve on top of it, upside down, such that the origin here will be at a distance which corresponds to the total charge of the system. That is, this charge plus this charge. Okay? Plot it from here. And here it is. I've taken this one, this curve, plotted here upside down, and then this is the original charge on the linear capacitor, this is the charge on the nonlinear capacitor, and this is the sum of the two. This was the voltage of the nonlinear capacitor, this was the voltage of the linear capacitor. Now we have an intersection, which means that this is the voltage of each of them after this connection. So Vt, this voltage, is the final voltage after connection. And once I have this point, I can actually look at the charge on each one of them, because if I have the voltage, then the charge is, of course, this height for the linear capacitor, and the charge for the nonlinear capacitor is, of course, from this point down on this curve. So this is one charge, and this is the other charge. So this will be a very simple way to get a solution of this problem that otherwise is rather complex to find, because you need somehow to approximate the behavior of this nonlinear capacitor by say a polynomial fitting or any other type of a fitting, and then solve in fact the nonlinear equations. Now what about the energy that has been lost? How can we figure this one out? Again, we have the initial condition. Initial condition meaning that we know what was the voltage and charge of the nonlinear capacitor, voltage and charge of the linear capacitor, and therefore we know what is the energy that we have started with. The energy of the linear capacitor is, of course, just CV squared over 2. The energy of the nonlinear capacitor, we have to go to this curve of energy as a function of voltage, and this will be the energy of the nonlinear capacitor that we have started with, this energy here. Now, after connection has been made, after the switch is turned on, we get different charges, different voltage. We can now calculate again for the linear capacitor in a very simple way what is the energy, and then looking back to this curve, we can find what is now the energy of the nonlinear capacitor when it is now with a voltage V sub t after the connection. So this will be here. So in this case, the nonlinear capacitor has gained some energy. Obviously, the linear capacitor lost some energy, and of course, by looking at the sum of the energy to begin with and the sum of the energy at the end, we can find out how much energy has been lost. So this would be an easy way to figure out this problem. So this brings me actually to the end of this presentation. I thank you very much for your attention. I hope you have found this presentation interesting and that it'll be useful to you in the future. Thank you very much.